All right, we're going to start on focusing on individual types of questions that we can expect on the AP exam. So today we're going to look at accumulated rate of change. So if we remember from past classes, something like velocity is the rate of change of distance. So when we look at velocity, we said that was equal to the rate of change of distance. It's basically distance divided by time. So when we see that time part, that's telling us we're looking at a rate. So this is the rate of change of distance. Now, remember that if we had a velocity time graph, and there's a certain velocity, if I wanted to calculate the distance traveled, we would find the area underneath this graph. So we said that area would equal the distance traveled by this particular object. Well, in calculus, area is the integral. So if we take the integral of the velocity function, let's say something like this, we are going to get the distance traveled by that particular object. Well, that's the focus then today on accumulated rate of change. Anytime we get any sort of rate of change, if we take its integral, we can figure out the total amount of the quantity that was being changed. Let's look at something else. So let's say that your rate of pay is $20 an hour. So this is your salary, this is time. Let's say we're at $20 here, and your rate of pay is $20. Now remember, that is $20 per hour. So now if I want to find my total amount that I earn, I'm going to take how many hours did we work. So if we worked 5 hours, we take all of this area and we would get $100. So it's kind of a very simple question, but the idea in calculus is exactly the same as what we just saw with velocity. If I take the integral of my salary, the rate of change of my earnings, I will get the total amount that we've earned. All right, so we're looking for rates. Now it may say rate of change. Something else to just consider is this particular question here. In the question, they may not say that your rate of pay. They may just tell you that you're earning $20 per hour. So when you see something like per time, overtime, or per meter, or anything that's per, it is a rate. And then this concept of accumulated rates may help us solve this particular question. Okay, let's look at a couple here. Here we're told a tank contains 125 gallons of heating oil at time 0. During a time interval from 0 to 12 hours, heating oil is pumped into the tank at a certain rate, and we're given that equation, and at the same interval, heating oil is being removed from the tank. So calculus will often have two rates working together, stuff being put in and stuff being taken out at the same time. Now we're starting off, this is going to be 4 parts here, but we're going to start off by being asked how many gallons of heating oil are pumped into the tank during the time 0 to 12. So we want the total amount of oil that is pumped in. Now this is just being pumped into, so we're only looking at the first equation here. So I'm going to take the integral from 0 to 12 of HT. So this is simply a calculator type question. We're going to plug in 12 into my time, and we will get the total. Now it's a good idea when you answer this question to make sure that you're showing what it is you're doing. So give them some sort of equation. You don't have to write out the whole thing here. You can just put HT and that'll be fine. Now the rest of this is putting this into our calculator. So I'm going to my calculator now. All right, so I put h of t into my y equals. So I put this into y equals, and then we did the integral from 0 to 12, and I ended up here with 70.571 gallons. $70.571 gallons of oil were pumped in those first 12 hours. Okay, so same question, but part B says, is the level of heating oil in the tank rising or falling at time equal to 6 hours? And give reasons for our answer. Well, now we have to consider both parts. At time equal to 6 hours, we are adding oil, but we're also removing oil. So we have to look really at which one is being, which one has the larger rate. So I'm going to think calculus-wise. I'm going to go h of 6. What is our amount rate at which we're adding the oil? And let's subtract the rate at which we're removing the oil. And if I find both of those, if this ends up being a positive number, then the level is increasing. This one is larger. If it is a negative number, then our level is decreasing. So again, this is what we're looking, always a good idea. Show them some sort of equation about what we're doing here. So now I'm going to go to my calculator again. I'm going to do h of 6, and I'm going to do r of 6. All right. So I punch into my calculator, I get h of 6 is 5.395, and r of 6 is 8.319. So I can already tell that we're going to be decreasing because r of 6 is greater. If I actually do the calculation, 5.395 minus 8.139, I'm going to get negative 2.744. So I can say that the level of oil is decreasing. At 6 hours, we're removing more oil than we're adding. All right, part C, how many gallons of heating oil are in the tank at 12 hours? All right, so now once again, we have to consider both things that are happening. So during this interval, we are adding oil and removing oil. So we got to remember we're adding heating oil and we're removing heating oil at this rate. If I want the total amount that we've added, subtract the total amount that we've removed over that interval, I can put them together and say 0 to 12. So this is going to give me the total amount. Now, let's back up just a bit. The idea here is I took the amount of heating oil that we added and subtracted the amount of heating oil that was being removed. Now we can put both of those integrals together in this fashion. Now what we do have to remember, in the question we were told a tank contains 125 gallons at time equal to 0. So we already started with 125 and then all of this happened. All right, so now this is what we're going to do here. I'm actually going to split these two parts up. So let's do 0 to 12 of h of t, and we're going to subtract 0 to 12 of rt. So we're going to do, we should really have the proper notation in there. Okay, so that's everything that we're doing for this question. Now it becomes a calculator question again. All right, so if I just slide this up a little bit. Now some of these things we already have done, right? The 125 is a constant. In part A, we did this part. That was 70.571. And then now we're just going to subtract how much we removed. So really all I have to do is punch R of t into my calculator and take the integral from 0 to 12. So I've done that, and I get 73.545. So I'm now going to put all of these pieces together, and I get 122.025 gallons. All right. One more piece here. At what time is the volume of heating oil in the tank the least? Show the analysis that leads to your conclusion. It's basically showing our work or justifying what we have to do here. So we want to know when do we get the smallest amount of oil? Well, the smallest amount is actually going to occur when H of t is equal to R of t. So at that instant in time, the level is not going up or going down. Okay. So that's what we're looking for. So I've graphed both of these on my calculator. So let's just give you a quick preview here. I'll do, let's say we'll do H of t in green. So H of t is going to be in green, and that's looking like this sort of, okay, natural. We got 1 over the natural log here. So there's our function. And then we said in red here, I'll keep it in red, the rate of change. Well, this was a sine function that actually does something like this here and crosses over and keeps going. And 12 is actually kind of right in here. That's our 12 hours. So this is our 0 to 12 hours. So we can see that there's actually going to be 2 times here and here where they're going to equal each other. Okay? So we're going to find those two and then figure out if it's a maximum or a minimum. Now another way to think of this would be if we move this over, I'm going to get H of t minus R of t is equal to 0. So we're not adding or subtracting any of our heating oil. So that's what we're actually going to be looking for here. All right, so I've gone ahead on my calculator and found the intersection points. And this first intersection point here is 4.791. And this second intersection point here is 11.318. 11.318. So now we're just going to figure out at what point is it the least. So this is more analysis of what is going on here. So if we look at this first point here, up until 4.791 hours, we have more being added than being taken out. So the level is actually rising up until this point. Now at this point we're starting to take away more than we are adding. So now the level is going down. So if we think about the level of heating oil actually going up until this point, and now it's going down until we get to this point here, the least amount is going to be at 11.31 hours. So we're going to say volume, we can say, is a minimum at time equal to 11.318 hours. All right, let's try another type of question. So here we're told the number of gallons of a pollutant in a lake changes at a rate P prime T equals 1 minus 3e raised to the negative 0.2 root T. Now, T is measured in days. Okay, so they're giving us the information a little bit differently. First of all, they do use the word rate, and then they give it as the derivative. Okay, so that's one way they can give us that information. In the previous question, they just gave us the rates as a function. So here they're giving us the rate of the pollutant as a derivative with respect to T. We're also told that there are 50 gallons of pollutant in the lake right now, and the lake is considered safe if there's only 40 gallons of the pollutant. Let's see if we can work our way through this. Is the amount of pollutant increasing at time equal to 9? And let's go why or why not. Let's look at the rate at which the pollutant is changing at this time. Okay, so there we're going to do P prime of 9. There's the rate at which the pollutant is changing at time equal to 9 hours. So 1 minus 3 e raised to the negative 0.2 root 9. So we're just going to punch that straight into our calculator. When we do that, we actually get negative 0.646. So that is less than 0. Clearly, we are decreasing at this time. So the question says, is the amount of pollutant increasing? We can say the amount is not increasing. Well, let's not abbreviate. Is not increasing at T equal to 9 hours. Oops, 9 days. This is in days. All right, same question, part B. For what value of T will the number of gallons of pollutant be at its minimum? And we're going to justify our answers. Well, minimums occur when the derivative is equal to 0. So the rate is the derivative. Let's set that equal to 0. So that, again, just like the previous question where we had the rate at which it was added minus the rate at which it was being subtracted equaling 0, we're doing the same thing. We want P prime to equal 0. So we're going to set that equal to 0. Now this is going to be a calculator type question. So let's put P prime into our calculator and let's find that 0. Alright, so I punched P into my calculator and I actually had to do a little bit of work with my window. Because this is an E, we actually had this sort of function happening here, and it didn't look like it was getting to 0, and I changed my window quite a bit before we finally saw it cross over, and we are looking for this value right in here. So second function intersection, second function calculate, sorry, not intersection, second function calculate 0, and then we did our left boundary and our right boundary, and I found the intersection was at 30.174 days. So that's when it actually was 0. That's when it's going to, now we wanted to test it. So I'm going to put P prime and P, and I'm going to go from 30.174, and really we're just analyzing the graph. Before this they were all negative, and after this they are positive, so that is in fact the minimum value. Alright, part C. Is the lake safe when the number of gallons of pollutant is at its minimum? Justify our answer. So at this time, are we safe? So now we got to figure out the total amount of pollutant in the lake at this time. So the total is the sum of everything that has been happening. So the sum of P prime T dt. Now we're doing that from 0 to this time at a minimum, so 30.174. Now we also have to remember we started at 50. So we started at 50 and then we're going to add all of this. So we're punching this into our calculator and we're seeing hopefully it's below 40. If it's below 40, we can say that the lake is safe. So again, let's punch this into our calculator. I have this in my calculator already, so I'm going to do the second part of this. Second function, calculate number 7 from 0 to 30.174. So that whole area is below the x-axis, so it actually becomes negative 14.896. We started with 50, so if I do 50 minus that answer, I actually have, so 50 minus the 14, I end up with 35.104 gallons. So we are safe at this time. So we can say, yes, it is safe. Yes, the lake is safe. So we, again, had to do the accumulated rate to get the total amount. So anytime we're looking for a total, we're taking the integral. All right, one last question here. It says, an investigator uses the tangent line approximation to P as a model for the amount of pollutant in the lake. At what time does the model predict that the lake becomes safe? So we've done it as an integral to figure out when it's safe. How about the model? What does the model predict? So let's just get rid of this stuff here so we can draw all over this for part D now. We want the tangent line approximation. So at time equal to 0. So remember a tangent line, we need point and slope. So the derivative that we're given here is the equation for slope. So I'm going to put in my 0. Well, if I put in 0 up at the top here, this whole thing becomes 0. E to the 0 just becomes 1. 1 minus 3. My slope is negative 2. Now, if we go back, we're told that there are 50 gallons at time equal to 0. So the point that is on our curve is 0 and 50. So if we put together our tangent line, we get y, let's do it this way, y minus 50 equals our slope and x minus 0. And that then becomes negative 2x plus 50. So remember, this is y in this case is the amount of pollutant, and x is the number of days. Now we need this to actually be 40. We don't need it to go to 0. We need it to be 40. So just a quick analysis here. It looks like the tangent line approximation is saying x is equal to 5. When it gets to 5, now we'll be at 40. Okay, so the tangent line approximation in this case is not really good. Okay, so that's accumulated rate of change. I have some questions up. Go check those out, and then I'll post some answers tomorrow.